For topic two, we're going to look at interval notation and set builder notation. These are two different ways that you can represent the solution to a linear inequality in one variable. So we've already talked about the graphs, okay? Set builder notation and interval notation, not bad. I will say that typically interval notation is maybe a little bit more complicated than set builder notation. However, if you're struggling with interval notation, the tip I would give you is graph it. If you can graph an inequality, interval notation is so much easier. Okay, so what I have here is a table. Okay, and in this table we have we're told that A and B are just real numbers, and we have different inequalities, and then we have the graph of the inequalities, and then we have that solution represented in interval notation and set builder notation. I would say kind of breeze through this table at some point when you have time, but what I want to do is I want to kind of look at these inequalities, but with actual numbers. Okay. So instead of saying X is greater than A is just some arbitrary real number. We're saying let A be whatever you want. X is bigger than that. Well, let's go ahead and think about this with like an actual number. So let's say we have X is greater than 2. Okay, so that means X, the solution for this inequality, X can be anything bigger than 2. It can't be exactly 2, but it can be anything bigger than that. So if I were going to graph this, I would draw a number line. I would figure out where my endpoint is. I would use a rounded bracket, and then I would shade to the right. So this darker shade, whoa. I love my computer because it's what I have, but sometimes it does stupid stuff. And I don't think it's the computer. I think it's Microsoft Word, but sorry about that. We do what we can. We're happy to have the technology that we do have. So anyway, this darkened shaded region, that represents the solution. Okay, now that's just the graph. How would we write this in interval notation? This shaded region quite literally represents your interval. The far left is the smallest value that our solution can be, and the far right is the largest value our solution can be. So we know we have a tricky situation here because our values for the variable can be anything bigger than 2, but not exactly 2. But we still use 2 as our endpoint or our boundary point. We just have to tell the reader either to include it or not. So we would go ahead and start. You always want your intervals to read from left to right. So I would say, okay, well, I can go from 2 forever to the right. Well, what is forever to the right? In math, forever to the right, we use infinity. We can go from positive 2 to positive infinity. And then here's the thing, infinity is kind of an idea more than an actual number. It's not a physical like number. There is no value that represents infinity. It's the idea that there's always something bigger, okay? So I could be like, hey y'all, infinity, that's really just like 10 million. And somebody could be like, you're stupid, it's 100 million. And somebody could be like, y'all, it's a gazillion. And somebody could be like, no, 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 it's a gazillion and one. And then there's going to be somebody else that says, no, it's a gazillion and two. There's always something bigger. That's what infinity should mean for us, is like we can go forever in the positive direction. But because there's no exact value for infinity, we can never include it. So infinity can never, ever, ever have square brackets. Infinity always has to have rounded brackets because it can never be included because there's always something bigger. Now, for the reader, can we include the 2? The answer would be no, we cannot include the 2, so we put a rounded bracket, okay? And then set builder notation, it's easy. So we have our graph, we have our interval. Set builder, it's weird looking, but it's actually really easy to do. So for set builder notation, you start with those squiggly brackets, which are always the hardest ones to draw, but I am here to tell you I am not judging how beautiful your squiggly brackets are. I promise. I got a lot of things to grade, and how pretty your squiggly brackets, they don't even rank on my radar of things to be concerned with, okay? So what we do is we state the variable. So you start your squiggly brackets and you state the variable, and then you just put a vertical line. What this translates to is we're looking for values of X such that, and then we lay out the condition on the values of X. And the condition is that X is greater than 2. And that's it. So squiggly bracket, variable, vertical line, and then just state whatever the solution is, and then another curly bracket at the end. Okay, so that is the kind of like the trifecta for writing out solutions to linear inequalities in one variable. Okay, now we also have examples of X is greater than or equal to A. So if X is greater than or equal to A, some arbitrary number, We would graph it by figuring out where A is. We would put a square bracket. I'm going to make it a little darker so you can see it. And then we would shade to the right. Notice this represents exactly our interval. Interval notation should read from left to right, smallest to largest. What's the smallest value our solution can be? A, including the endpoint. And then we can go forever to infinity, and we never include infinity. Okay? Looking at the third inequality, we have x is less than b. So b, again, is just some arbitrary number. Okay? Now be a little bit careful with this one because we still have an infinity, but we're looking at infinity on the other side of the number line. Okay, so looking at the graph, we would indicate where our boundary point or our end point is, and then we would use a rounded bracket. And then this time we want to shade to the left. So this says values for x can be anything less than b, not including exactly b. Okay, and that's exactly what our interval should say. So from left to right, we can go forever to the left all the way up to b, not including b. So what is forever to the left? Well, forever to the left is negative infinity. And again, it's this idea that there's always something smaller. So no matter what number we throw out there as the smallest number, somebody can always subtract one from that and make it smaller, or add one to that and make it smaller, however you want to think of it. All right, so there's always something further to the left. So our interval, reading from left to right, is going to have negative infinity. We can never include it. And then we're going to go all the way up to the largest value our solution can be, which is b, but we can't include that, okay? And then just put a comma between the highest and lowest values. So the left is the lowest value in your solution set, the right is the highest value in your solution set with a comma between them. And then finally, we have the same thing, but x is less than or equal to b. So we would go from negative infinity to b, square bracket this time. And then for our graph, it would be the same thing. We would indicate our boundary point B. We would put a square bracket on it, and then we would shade to the left. And there's nothing weird about interval set builder notation. Squiggly bracket, state the variable, vertical line, and then whatever the condition on the variable is. Okay, so for the next example, I think we have, yeah, we just have one example here. So for example 2, it says graph each inequality and then represent the solution in interval and set builder notation. So first we have x is greater than or equal to 3. So what I want to do is I want to find 3 on my number line. Okay, so I can see that 3 is right here. All right, and then I have to ask myself, can I include exactly 3 in the solution? And the answer here is yes, because values for x can be greater than or equal to 3. So I want to put a square bracket on 3, and then to indicate that we're looking for values that are 3 or bigger, we would shade to the right. And this shaded region is your interval, okay? So looking at my interval, do I have am I starting with an arrow or am I starting with a bracket? We're starting with a bracket. It happens to be square. So start with a square bracket, put whatever the endpoint is, 3, put a comma, and then is the second value a bracket or is it an arrow? It's an arrow, we're going to the right, so infinity, and infinities always get rounded brackets, okay? And then set builder notation, we start with curly braces or curly brackets, state the variable, vertical line, so this says we're looking for values for x such that, what is the condition on x? Well, the condition is that x has to be greater than or equal to 3. Okay. And then for part B, we have just a different inequality. We have x is less than negative 1. So going to our number line, we want to find negative 1, which is right here. We have to ask ourselves, can we include exactly negative 1 in our solution? And the answer to that would be no. Okay, x has to be strictly less than negative 1. So negative 1 truly is a boundary point. We can't include it. All right, so to tell our reader that, we're going to put a round bracket on negative 1. And then we need to indicate to our reader that anything less than negative 1 is fine. So on a number line, less than would head to the left. So we're going to shade to the left. And then this is exactly what our interval is going to look like. So from left to right, do we start with a bracket or an arrow? We start with an arrow, so that says we're going to start with an infinity, so negative infinity in this case, comma. How high can we go on the number line? Well, to negative 1. But the question is, can we include negative 1? Heavens no. So we put a rounded bracket, and then same thing, can we include negative infinity? No, we can't. So rounded bracket. And then set builder notation. Squiggly bracket, state the variable such that, and then just lay out the condition on x. The condition is that x has to be less than -1. And that is set builder and interval notation for inequalities. So when you're dealing with an inequality, because the solution is no longer just a single value, it's this entire interval of values, we have to find a way to represent all solutions, all values that satisfy the inequality. So we can do that with a graph, we can do that with an interval, or we can do that with set builder notation. Okay. So in the next video, I think we start, yeah, in the next video, we're going to start solving inequalities. And the good news is there are a lot of similarities in solving linear inequalities and solving linear equations. There's really just one big difference, and we'll talk about that in a bit.